Okay, 3.2 is measures of dispersion. In 3.1, we discuss measures of central tendency. So those measures describe the typical value of a variable. In other words, the quote-unquote average, right? But we would also like to know the amount of dispersion in the variable, or how much the data is spread out. So first of all, let's look at this example. To order food at a McDonald's restaurant, one must choose from multiple lines, while at Wendy's restaurant, one enters a single line. The following data represent the wait time in minutes in line for a simple random sample of 30 customers at each restaurant during the lunch hour. So for each sample, answer the following. And just to save time and effort, on this at a video, I've already calculated it. But first of all, it asks us, what was the mean wait time? Well, we know from the last section to find the mean, I would just add all these up and then divide by 30 because there's 30 values. So the wait time at Wendy's mean is 1.38, right? At McDonald's, it's 1.38 ... So both of these would round to 1.4. 1.4. Same mean. But let's look at the histograms of the data, right? Here's wait time, and we said the mean is 1.4. So basically, the mean is right here. So notice most of the values at Wendy's, or at least way more of them, are pretty close to this mean. These values at McDonald's, there's a bunch of them that's way spread out. Look how many are here, right? And then how many are down here. So the histograms suggest that this data is more dispersed, right? More spread out. And the goal of this section then is to discuss numerical measures of dispersion so that the spread of data can be quantified. There's three numerical measures for describing dispersion or the spread of the data that we're going to discuss: the range, the standard deviation, and the variance. Okay, so the simplest measure of dispersion is the range. The range, which we'll call cap R, of a variable is simply the difference between the largest data value, the maximum, and the smallest data value, the minimum. So that is, to find the range, we just take the difference, the maximum minus the minimum. So if we wanted to find the range of the following data, which is travel time in minutes to work for all 7 employees of a startup web development company, we notice that the largest value is 43. The smallest value is 5. 43 minus 5, 38. That's the range. Okay? Now notice the range is affected by extreme values in the data set. For example, if this would have been 83, the range is dramatically affected, right? It would change to 78 just from changing one value here. So it's not resistant. Remember, we talked about being resistant last time. Also, the range is computed using only 2 values in a data set, and the next one then, the standard deviation, okay, uses all the values in a data set on those comparisons. Okay, so measures of dispersion are meant to describe how spread out data are. In other words, they describe how far, on average, each observation is from the typical data value. Standard deviation is based on deviation about the mean. Okay, so the population standard deviation of a variable is the square root of the sum of squared deviations about the population mean divided by the number of observations in the population, cap n. That is, it is the square root of the mean of the squared deviations about the population mean. Blah, 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 right? Okay. Sometimes our definitions are a little hard to read through, but once we show the example, maybe it'll be more clear. Okay, so here's the formula. Okay, this symbol right here is a lowercase sigma. And remember, when we're talking about parameters, we usually use Greek letters. And so sigma is represented by the population standard deviation. So what this says is we're going to take the square root of each data value minus mu, the mean squared. We're going to add each one up, divide by n. Remember this symbol from when we were talking about the mean, that's the capital Greek letter sigma, and it's read the sum. So just like we can just simplify, instead of having these plus signs and all spread out, we can just say sum them all. Okay, where of course our x sub 1, x sub 2, dot, 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 x sub n are our actual observations. Now, we also have a different formula. It's equivalent to the same one. It just had some algebra done on it, right? And they call this the computational formula. So we could also use this to find the standard deviation for the population if it's sigma. Okay, so notice the difference in this terminology. This one is saying, okay, sum up all the squares of the values. This one is saying take the sum of all the values and then square it, right? So be really careful about the difference in our notation. All right, let's look at an example of that. Okay, it says the following data represent travel times in minutes, again, to work for all 7 employees of a startup web development company. Compute the population standard deviation of this data. So I need a table to do that. If I just have a few, I'm going to do it in a table. In a minute, we'll talk about how I'm going to do that on the computer, but on the calculator. Okay, so first of all, I'm going to list my time, right? These are our x values. So I'm just going to list them. 23, 36, 23, 18, 5, 26, and 43. Now, I need to find my mean, so let me get my calculator. And it helps to turn it on before you start trying to use it. Okay, so 23 plus 36 plus 23 plus 18 plus 5 plus 26 plus 43, all divided by 7. Okay, so mu is 24, and it leaves several decimal places, 0.8571. Okay, so then I'm going to have a column. My next column is going to be each x value minus mu. So I'm going to say 23 minus 24.8571. Okay, that gives me negative 1.8571. 36 minus 24.8571, which gives us 11.1429. 23 minus 12, we've already done that one, negative 1.8571. Okay, what about 18 minus 24.8571? Negative 6.8571. How about 5 minus 24.8571 to get negative 19? 0.85971. I don't know where that 9 came from that I spoke. It's not actually in the number 8571. Okay, 26 minus 24.8571. 1.1429. And finally, 43 minus 24.8571 to give us 18.1429. Now, something at this point, this isn't part of the process, but just something I want to point out to us. I'm going to add these values up right here. So 18.1429 plus 1.1429 minus 19.8571 minus 6.8571 minus 1.8571 plus 11.1429 minus 1.8571. And if I do that, I get this. 0.0003. Basically 0. Technically, I would get exactly 0, except for due to rounding. I've got a little rounding error down here. Okay? So think about what that means. I should always get 0 here. Always, always will I get 0 here because remember what we said about the mean. It's the balance point. Okay? So all of these have to be, when I add them up, it's got to add to 0, right? The distance from each point from the mean, there's just as much weight on one side of the mean as on the other side of the mean. So every single time we find how far each point is away from the mean, the average of that's going to be 0 because the mean is the balance point. So to get away from that always being 0, let's go back and square all of those numbers. Okay, so 1.8571 squared is 3.4488. $11.1429 squared is 124.1642. 1.8571 squared is 3. Oh, we already did that one. Okay, 6.8571 squared. And yes, once you had that calculation here, if you'd have just squared it and gone ahead, it'd have been a lot shorter work. But, you know, in the first process, we're just talking about where these values are coming from. So 47.0198, 19.8571 squared is 394.3044. 1.1429 squared is 1.3062. 18.1429 squared is 329.1648. Okay, now it's really this that I'm going to add up. So now I'm going to take basically the average of this. So I'm going to add all of these values up. So 3.4488 plus 124.1642 plus 3.4488 plus 47.0198 plus 394.3044 plus 1.3062 plus 329 0.1648 to get, we get 902.857 by adding that up. Okay, so now what that means is I'm going to divide this by n to take the average, but since I squared these numbers, then to undo that square, I'm going to take the square root. So really, I'm going to do the square root of 902.857 divided by n, which in this case is 7. And yes, I could divide this by 7 and then put it in the square root, but once again, the more and more you round, the farther off you get from your value. So I'm going to do the square root all in one step of 902.857 divided by 7 for 11.36, rounded to 2 decimal places. Always pay attention to where they ask you to round. And that's sigma, or the population standard deviation. Okay. All right. I think I'm going to write that down. I think I need that value in a minute. So I'm going to write that down. 11.36, so we can refer back to it. I think, if I recall. Okay. All right. And now we have the sample standard deviation. Okay. It's the exact same formulas, right? Except for our data items come from a sample. So notice we would call it S. Okay. No more Greek letters if it's from a sample. And notice I divide by n minus 1 instead of n. Okay, showing why we divide by n minus 1 is way beyond the scope of this introductory course. We're just going to, just go for it and understand that the statisticians have come to find out that that gives us a much better approximation of the actual standard deviation. And so we call n minus 1 the degrees of freedom, because the first n minus 1 observations, in other words, all of them except the last one, have freedom to be whatever value they wish. But the nth value has no freedom. It must be whatever value forces the sum of the deviations from the mean to be 0. Okay, technically that's not going to be that important for us, but that n minus 1 is called the degrees of freedom. So be sure you divide by n minus 1, not n, and be sure you use as many decimal places as possible to avoid round-off errors. Okay, so here now it wants us to compute a sample standard deviation, okay, which is exactly the same. The only difference is we're going to call it S. Okay, so let's just, for practice sake, do it again. So we list all of our data values. Okay. And then we're going to subtract the mean. So let's find the mean for this. 26 plus 36 plus 5 divided by 3. The mean is 22.33. And let's leave several decimal places. All right, so we have 5 minus 22.3333, which is negative 17.3333. And since I know now that my next column is actually going to be this squared, while I have that on my calculator, I can just square it, right? Saves me going back and re-entering 300.4433. Okay, now we have 26 minus 22.3333 to get 3.6667. If I square that, I get 13.4447. 447. And 36 minus 22.3333 gives me 13.6667. And squaring that gives us 186.7788. Notice if we add this together, look, 13, 16, and then this is 1 1/3, 17 1/3. This would equal 0. Okay, just as kind of a double check. Okay, so let's add these up. Plus 13.4447 plus 300.4433. Okay, so we get 500.6667. Now, I'm going to take the square root of that, but I'm going to divide by not 3, but 2. N minus 1, right? Don't forget that. So now I'm going to say, well, what is the square root of 500.6667 divided by 2? 15.82. Okay, now this is S, or standard deviation on a sample. Okay. Okay. So let's go back and talk about that beginning example we talked about between Wendy's and McDonald's. It says determine the standard deviation, okay, at which I'm not going to go back and redo it. I've already done it to save us time here once again. It says which is larger and why. So the sample standard deviation for Wendy's was 0.738 minutes and for McDonald's 1.265. Recall from earlier that the data is more dispersed for McDonald's, which resulted in a larger standard deviation. I'm going to fly back up there right quick. Okay, there it is. McDonald's, remember we said here's the main, okay, and there's a whole pile of them, right, 2 bars away, and then all of these are spread several bars away. Here on this main, most everything is 1 bar away. There's just a few outlined. Okay, so if we're comparing 2 populations, the larger the standard deviation, the more dispersed the distribution is. Okay, and also the units that we use to measure, they have to be the same so that we're comparing apples to apples. So don't forget, if I'm doing minutes here, I've got to be doing minutes here. Okay, a third measure of dispersion is called the variance. So here's the variance. The variance of a variable is the square of the standard deviation. So the population variance is sigma squared and the sample variance is S squared. Okay, so it says the following data represent the travel time in minutes to work for all 7 employees. Compute the population variance. Okay, this is why I saved that standard deviation earlier. We had 11.36, and to get the variance, all I have to do is square that. Okay, so now you might also notice we get this value as our last step of calculating the standard deviation. So if I need the standard deviation and the variance, I get it all in the same process. Okay, so make sure if you are doing this to get your variance, if you find your standard deviation first, try to have as many decimal points as possible here, okay, because you're going to have rounding errors if you don't. Okay, the units of measure and variance are squared values. So for example, this is square time, okay? So it makes interpreting the variance a little difficult, but it's important for conducting certain types of inference that we're going to do later in the text. So we are going to use this variance later, but be aware that your units would be like square time, square dollars, which is a little bit unusual. Okay, now we have the empirical rule. Okay, notice we have a big if a distribution is roughly bell-shaped, then approximately 68% of the data will lie within one standard deviation of the mean. Okay, approximately 95% will lie within two standard deviations, and approximately 99.7% will lie within three standard deviations. Okay, note, of course, we can also use the empirical rule based on sample data with X bar instead of mu and S instead of sigma. Okay, so again, that's a lot of wording. It's like, what does that mean? It's much easier to understand to just be shown. So here is an illustration of what that means. So notice our graph and notice what it is. It's that bell-shaped curve we've been talking about, and it's symmetrical. And if it's perfectly symmetrical, the median and the mean are the same value. Sorry, the median and the mean are the exact same value. So the empirical rule tells us, it's also sometimes you hear as the 68, 95, 99.7 rule. And I need to know those numbers. I need to remember those numbers. We're going to use them like crazy. It's going to be important. So we calculate the mean and the standard deviation. And then what that says is 68% of your values are within one standard deviation of the mean. For example, let's say we had some kind of population. Let's say we're talking about IQs, and we say, oh, well, the mean IQ is 100, right? And the standard deviation is 20. So that means we would add 20 again, add 20 again, and then we would subtract 20 again, subtract 20 again. So 68 of the population, and again, I just made these numbers up, 68% of the population would have IQs between 80 and 120. 95% of the population would have IQs between 60 and 140. And 99.7% of the population would have IQs between 40 and 160. Okay, so that's what the empirical rule is telling us. So let's look at an example of that. Okay, using the empirical rule. So the following data represents the serum HDL cholesterol of the 54 female patients of a family doctor. Okay, so we've got all of this that we want to do, but the first thing is compute the mean and standard deviation, right? And it's telling us its population. Okay, so we'll just be dividing by n. That's why that's important to know. So compute the mean and the standard deviation, and then draw a histogram, and then blah, blah, blah. But first, let's go back and compute the mean and the standard deviation. Now, look how much data there is. I really do not want to make a chart that has that many rows, right? So now I'm going to move to my calculator. Okay, and remember, there's a module in your, what did I call it? Technology tips from the text. that will help you if you have a TI 83 or 84, so I hope you do, that'll help you figure out how to use your calculator to take care of a lot of this that we're going to cover. So I'm going to do that now. I'm going to use my calculator on this. Okay, so what I do for my calculator, I have the 83 plus, and the 83 and 84 are basically the same. So first I'm going to go into stats, right, and then I'm going to edit and go over to enter my data values. Okay, so I'm just going to enter these values: 41, 62, 67, 60, 54, 45, 48. Just entering these values in my list in the calculator. All right? So if you need to pause this and go look at that, actually it's a picture. I just took a picture of the instructions inside the text and put them in that technology tips. Okay, so that you can catch up with us. Okay, I'm going to enter all of this data, and I'm talking at the same time, so hopefully I'm not making a mistake. Okay, 54, 74, 64, 59, and finally 53. Okay, so I got all my data entered in there. Okay, then I'm going to go back and I'm going to hit Stat, go over to Calc for Calculate, choose the one variable statistics, and it comes up with my X bar, the sum of my X's, the sum of X squared, right? And then my sample and my population standard deviation. So let's see what exactly it was. Where's my pen go? Okay, that we're trying to do here. Okay, compute the population mean. Okay. So no, sorry, pen. My mean is 57.407. And standard deviation is 11.696. Okay, it says draw a histogram to verify the data is bell-shaped. Okay, because remember, this empirical rule only works for bell-shaped data. So I'm going to leave that on our screen there. Hopefully it won't be too bad in our way now. And let's go back here because I need to see this to draw my histogram. Let's say I've got data values 35 to 85, it looks like. All right. So again, since I'm just drawing this for my own personal use for verification purposes, let's say maybe I'm going to go 35 to 39 to 44 Uh-oh. Well, let's squeeze it in. All right. Let's see, there's 54 results, so maybe let's go by fives. Okay, So 35 to 39. One, two, three, four, four. Okay, so this bar is going to be about that tall. 40 to 44. Remember, there can't be an overlap, so I can't do 45, 40 to 45, and 45 to 50, right? So it's 40 to 44. 1, 2, 3, 4, 5. So 5, so just barely bigger. Okay. My scale is awful, sorry. So 45 to 49. 1, 2, 3, 4, 5, 6, 6. So just a little bit bigger. So we will have room. I'll just have to do this a little better down here. Okay. See if that's better. Because my bars need to be the same width, remember? All right, so 50 to 54. 1, 2, 3, 4, 5, 6, 7. 55 to 59. 1, 2, 3, 4, 5, 6, 7, 8. 60 to 64. 1, 2, uh-oh. So one more, so 10. I was at 9, wasn't I? So really that's 10. Now 60 to 64. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 again. 65 to 69. 1, 2, 3, 4. 70 to 74. 1, 2, 3, 4, 5. 75 to 79. 1, 2. And 80 to 85. 1, 2. Okay, so the question is it symmetric? Roughly, right? Okay, so since it is symmetric, roughly, let's see what else it's asking us to do. Okay, determine the percentage of all patients that have serum HDL within 3 standard deviations of the mean. Oh, well, that's automatically 99.7. I don't even have to draw it or anything. Oh, shoot. Shoot. I hit the wrong button. Okay, well, I'm gonna have to go back and, oh no, I probably still have it on my calculator. Yay. Okay, so because it is roughly bell-shaped, then that means the empirical rule can be applied, and automatically I know the 68, 95, 99.7 rule, right? So that's just 99.7%. Now, to use the empirical rule, I'm going to draw a rough sketch, always exactly the same. Okay, where I'm going to put the mean here. Okay, and let's see, yeah, it's still on my calculator. So the mean was 57.4. And then I'm going to add, let me write that down because it will disappear once I do something. So 57.4, and then the standard deviation is 11.7. 11.7. So I'm going to add, I'm going to take the 57.4 and you add 11.7 3 times. So the first one gives us 69.1, and then add 11.7 again, 80.8, add 11.7 again, and 92.5. And then you subtract it 3 times on the other side. So I'm going to go back to 57.4 and I'm going to subtract the 11.7 to get 45.7. And I'm going to subtract it again to get 34. And I'm going to subtract it again, 11.7, to get 22.3. Okay. Now, the question says, determine the percentage of all patients that have serum HDL between 34 and 69.1. Okay, look, that's right here. Okay, so I'm going to mark this that we're doing that in red. So let's put our values up there. We know that between these two is 68% of the data followed between those two. Okay. Whoops. Sorry. This is 95% of the data. And this is 99.7% of the data. So this question up here could have just as well have said, right, determine the percentage of all patients that have HDL between 22.3 and 92.5, right? But that's within 3 standard deviations. Okay, so if this just said between 45.7 and 69.1, if it said that, oh, I know it's 68. But I've got to do a little bit of calculating here, right? Because what I'm doing is I'm looking up each value, and wherever the arrow ends that I'm interested in, okay, I've got to think about that. Okay, so in order to do this now, let me use a different, let's see if I can do yellow. Yellow. All right, so this is the mean. Okay, so notice what that means. Half of 68% is this much. So I know that that's 34%. Half of 68%. And then this chunk over here is half of 95%. Half of 95, what's that? 47.5%. So if I don't have the two specific values that go with the empirical rule, if I do, I can just look at it and say, oh, 68%, ooh, 99.7, right? But if I don't, I've got to break it down and do some calculating. So now I know that this piece is 47.5% because it's half of the 95, right? And this piece is 34% because it's half of 68, because that's what it means to be the mean, right? If it's normally if it's a bell shape, and then we'll call it normally distributed later, okay? But if it's bell-shaped and symmetric, the mean and the median are the same. So this is right smack dab in the middle. Okay, so then that makes this final answer, what does that make that? 81.5%. Okay, let's do it again. This time it wants to determine the actual percentage of patients that have HDL between 34. The actual percentage of patients between 34 and 69.1, right? So this said according to the empirical rule. So let's leave that 81.5, and then let's go back and determine the actual percentage. Let's see how we can do that. Okay, I'm going to erase all this and put that 81.5 back. All right, 34 and 69. Between 34 and 69. Okay, so 69 is going to be included. 34 is not, because it says between there. Wrong way. Okay. Technology, sorry guys. Or old people trying to do technology, I guess I should say, right? Okay, so here's what we would do to find the actual percentage. Okay. Grief. Come on, pen. Okay. 1, 2, and just to give us a reference down here, I'm going to go 35 to 69 is what I'm counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43. 43 out of the 54. Let's see what that is. 43 out of 54 is 79.6. Okay, pretty close. Basically 80, 81 and a half. Okay, so within 2 percentage points. Okay, so that's the empirical rule. Okay, let me know if you need any help with that. Okay. Chebyshev, right? He was a Russian mathematician, and he developed an inequality that determines a minimum percentage of observations that lie within K standard deviation, some number of standard deviations, okay, of the mean. Now, what's amazing about this one is that the result can be obtained regardless of the basic shape of the distribution. Okay, so here's what Chebyshev's inequality says. For any data set or distribution, anyone, at least 1 minus 1 over k squared times 100% of the observations lie within k standard deviations of the mean, where k has to be greater than 1. Okay, so that is at least 1 minus 1 over k squared times 100% of the data lie between, right, mu minus k times sigma. This is the same notation we had on that empirical rule. And of course, we can also use it, excuse me, on sample data. So let's see what that means. Use the data from the previous example. Use Chebyshev's theorem to determine the percentage of patients that have serum HDL within 3 standard deviations of the mean. Okay, within 3 standard deviations of the mean. So that means I need a pen. Okay, so his formula, K in this case is 3, looks like this. Okay, that's it. Where however many standard deviations you're being asked, you just plug into that formula. Now let's see what that gives us. 1 minus 1 over 1. Wow, 88.89%. Wow. And then it says go back and determine the actual percentage of patients that are between 34 and 81. Okay, so that would be 35 to 81 this time. No, to 80. 35 to 80. But we'd go back and do the same thing. Count up exactly how many. And we already did that really close. We did 35 to let's just go back and do it, 35 to 81, and we have, here's what Chebyshev's is telling us. Okay, 35 to 81. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 1, 2, 3, 4, 45, 46, 47, 48, 47. All right, I got a little carried away there. So we're on 47. Excuse me. 48, 49, 50, 51, 52, 53. 53 out of 54 is really 98%. Okay, so notice the results aren't exact here, but also notice, okay, so we've got 98 versus basically 89, but let's go back and look at that formula. Notice it says at least. At least. So it's not saying that that's an approximation for how many are within there. It's at least that. So he said 89 or more, and we could see it was 98, right? So remember, the empirical rule holds only if the distribution is bell-shaped. Chebyshev's holds regardless of the shape of the distribution, right? But because um, the empirical rule gives more precise results, we really prefer that. But we have to have a bell-shaped, basically symmetric distribution to use it. Okay, let me know if you need anything.